So, first part here is a review from last lesson, simplifying. Okay, so remember I have up here all the perfect squares, and these are the perfect cubes. Okay, so perfect squares, you want to look for the biggest factor of 27 that's a perfect square. So obviously you're not even going to look past here. So what goes into 27 evenly? 9 does. So remember, the way I like to show it is show it as a multiplication of the perfect square times whatever other factor it is. Then I circle the perfect square. It gets to go out on the weekend, leave home. It's worth a 3. The other 3 stays home. Okay. Remember that you can check with your calculator. Or you can check second. I'll just go check on that. So I said 27, and then 3 root 3. Okay, they're the same value. All right. Next one, root of 125. So again, you'll want to look for perfect squares. So really, 121 is past there, but none of those go in. You want to keep going. If it has an ends in a 5, then you know you want to end in a 5, right? So the only one would be 25. So that's 25 times 5. Circle the perfect square. It gets to go out on the weekend. Left with 5. Now, just by chance, it's happened that these two numbers are the same, okay, and those two numbers are the same, just because of that particular number. Okay? It's the process you have to follow, looking for the perfect square that's a factor. Next one, notice how it's a cube root. So cube root, you have to look at the perfect cubes. Less than 40. Well, there's only 3 that are less than 40, and 1 doesn't give you anything, right? So you don't even consider that. If 1's the only perfect square that's a factor, you can't simplify anymore. So 8 is a factor. Remember to copy out the little 3, so that's 8 times 5. And now the perfect cube gets to go out on the weekend. And the 5 stays home. Okay, with the little 3. Okay, so a little bit of an extension here. Now we have a number in front. When you have a number in front, that means multiply. Okay, if there's nothing shown there. So it's 3 times whatever the square root of 20 is. So this is 3. I'm still going to look at 20 for the biggest perfect square. That's a factor of 20. So you look here, 4. All right, 4 is the biggest one that goes into 20 without a remainder. All right, now when you bring the 4 out, it's a perfect square, it gets to go out. If I show it like this, then that looks like it's 32. Okay, it's not. This is 3 times. So it should be 3 times 2. You could put it in brackets or just use a multiplication symbol. And so really that's 6 root 5. Okay, so when you bring it out, just don't put it to the right of 3. You can't just add a digit to the number. Okay, it needs multiplying. So again, you can check. So 3 square root 20, okay, value in that. And then when I simplify that, 6 root 5. And I get the same thing, so I know that I've simplified. There are cases where maybe you get the exact same number, but it's not completely simplified. That would be if you have a big number that you haven't found the largest perfect square, only one of them. Okay, so you do have to be careful with that. Next one, again, that's 4 and 18, we want to simplify. So you want to look at your biggest perfect square that's a factor. It would be 9. Circle the 9 because it's a perfect square. Root of 9 is 3. Okay, so again, it's not 43, it's 4 times 3. Root 2, which is 12 root 2. Okay. If you want to put this in brackets like this, same deal. Okay, you can only multiply the coefficients, the integers outside. Well, they don't even have to be integers, they could be rationals, any decimal, fraction, integer, whatever. You cannot multiply these numbers with the 2 without squaring it back. And we'll talk about that in a minute. Okay, and then 5 root 80. So, take a look here. You might think, oh, okay, 4 goes into 80. Okay, it does, but it's not the largest. Okay, so 80 is up here. You want to think, okay, does 64 go in? No. 49, no. 36, if you're not sure, you can start trying, right? So 80 divided by 36 will go in, right? It's not a whole number. 80 divided by 25 is not going to. 80 divided by 16 goes in 5 times. Okay, so now you know that's 16 times 5. So that's when you can use your calculator to help you. Okay. Circle the 16. And again, you can use brackets or the multiplication symbol. That's 4 root 5. And so that's going to be 20 root 5. Okay, so that's simplifying. And you're getting the radicand, the number underneath the radical sign, as small as possible. Now, we're going to do the opposite. We're going to convert from a mixed radical to an entire. So that's the opposite of what we were just doing. So think of what we were just doing, though. In any of these, if you're simplifying, I'll go back to the sort of the more basic ones. We were splitting this up into a perfect square times any other number, whatever is the biggest perfect square. When that comes out, it's worth 3, the square root of 9. So when it comes back in, it's worth 9. You have to square this to come back home, right? So when this went out of the house, out of the roof there, it's square rooted. When it goes back, you have to square it. This comes out, it's 5. When it goes back, it has to be 25. So that's what you do when you want to express as an entire radical. Entire means no number outside of the root sign. Okay? So this, when that goes back inside, is worth 4. Okay? 2 squared is 4, and the 5 is already there. Okay, really we don't have to show it in 2 separate steps. Remember, we did that in the first time when we were simplifying, but we don't have to now. So that's 4 times 5. That's really what my first step usually is. And then 4 times 5 is 20. Okay, so mixed radical to entire, this, no number outside. Can't have it anymore. So you square it to put it back in. So here, now we're going to have a big root sign, radical sign. 5 to go back in. Is 5 squared. You can even show it like that if you want. Times 10, which is really 25 times 10. So that would be really what your first step could be. And then that's root of 250. Okay, so you don't have to show 3 steps. I would show 2 steps. Square of 5 in your head is 25, times the 10 is 250. Okay. Okay, so square of the 4 is 16 times 3. So when you think about, in some radicals, we show the index. Square root, we don't have to, but it's a little number there. It's kind of like taking that as an exponent on the coefficient. Okay. And always remember, these are not the index. This is a big number. It's out front there, so it's not a cube root. It's 3 times square root of 7. So that's 3 squared is 9 times 7. 63. So when you check something like that, you're going to have 3 square root of 7, and then square root of 63. You get the exact same. Okay, so you know you haven't switched them around. You can do the same with cube roots, but we don't have any examples there for now. You'll do that for sure in 10C. All right, so some other properties. How they relate. So how do radicals relate to fractional exponents? So use your calculator to evaluate each of the following round to the nearest hundred. So enter root 2 in your calculator. So root 2 is 1.41. And then 2 to the exponent is 1/2. So on a graphing calculator, most calculators, it's a little arrow key. Sometimes it's an x to the exponent y. Sometimes it's y to the exponent x. In any case, there. In a newer version, it actually goes up in the high position. In some calculators, it just shows that symbol. Okay? And then you can just go 1 divided by 2. You can put it in fraction form, but that's a waste of time. That's a half. Okay? And you see, you get the same thing. So root 2 is the same as 2 to the 1/2. Let's try for the next one. So root 3, and then 3 to the 1/2. You get the same thing. We do. Square root of 4, hopefully you know that already, it's 2. You didn't know what 4 to the 1/2 is though, so 4 to the exponent 1/2, it's 2. Okay, so that means when you're taking the square root, so when you're taking the square root, it's the same as raising it to the exponent 1/2. Okay, so from the tables above, what can you conclude about the exponent 1/2? It is the same as taking a square root. Right, so that 2 in the denominator of that half really means that you're taking this square root, 2 equal factors of the radical. Okay, so sometimes it's easier to show numbers with the fractional exponents. Sometimes radicals are easier. Just need to know that they are the same. Okay, so now it says evaluate each without a calculator. You can check, but let's think. What I just said was, turn over your page. There's some graphics there. We decided that when you raise something to the exponent 1/2, it's the same as taking the square root. So really, you're taking the square root of 9 here, right? Which is 3. Don't need a calculator. Here's square root of 25, which is 5. Don't need a calculator. square root of 49, which is 7. Okay? Now, another way to show that is breaking down the radicand into a power, right? So you could actually, this is the same as, so this 49 is 7 squared. So if I replace 49 with 7 squared, raise it to the 1/2, then we know our power loss, power of a power, multiply the exponent. Well, 2 times 1/2 is 1. So that's 7 to the 1, which is 7. Okay? So we already knew square root of 49 is 7, but for bigger radicands, bigger powers, that kind of thing, you may end up simplifying using the exponent loss. Okay? And again here, let's look at this aspect of it. If we look at the exponent of 1/2 in more detail, use your loss to simplify the following. So 6 to the 1/2 times 6 to the 1/2. Multiply powers with the same base. You add the exponents. Well, 1/2 plus 1/2 is a whole, right? That's 6 to the 1, which is 6. Okay? Now use radicals to show this is true. So root 6 times root 6. Okay? Well, if you're multiplying radicals like that, you can multiply the radicands together. There's nothing outside, so that's root 36, which is 6. Okay? So this is the same as this. So fractional exponents, radical expressions give you the same value. Okay. All right, and then really in 3 and 4, you're just switching the way that you show it. You're not even evaluating anything. They're not perfect squares, nor is there a factor that's a perfect square. You're just showing it in different ways. So here, show it as a power. That's 15 to the 1/2. Right? It's square root. So that's a power form. Don't evaluate. So you're not calculating anything, you're just showing it in a different way. So this would be 55 to the 1/2. If that was a cube root, it would be 55 to the 1/3. Right? Whatever the root is the denominator of that fraction. So vice versa here, show as a radical. So that's going to be square root of 22. This is going to be square root of 38. Just showing it in a different way. It means the same thing. Okay. So in question 5, we're going to evaluate. So we can think about order of operations. Brackets first, there's a square root of 9. So that we know square root of 9 is 3. And it's still raised to the exponent 4. It says evaluate, so find the value of that. That's 3 to the 4th. So I always think when it's exponent 4, I think 3 times 3 is 9. 3 times 3 is 9, so that's 4 of them. 9 times 9 is 81. Trying to get those mental math skills going. Okay. This one, I'm going to use my power of a power, right? So here, I mean, I could think about this. Just learn that raising to the 1/2 is like the square root of 9. So it's back to back, same as part A. Or we can show this as 9 to the 1/2 times 4 is 2. Well, 9 squared is 81. Yeah, the same thing. Now the next one, if you look at it, you might think, okay, I'm going to do 9 to the exponent 4, the inside in the radicand. So that's going to be square root of 6,561. And then I'm going to try square root. And you get back to 81. Okay. Same answer. All of these so far have been 81. And then this one here, again, power of a power. That's going to be 9 to the exponent 2, which is 81. Okay. So take a look. What's similar about them? Here, inside the brackets, is the exponent of 1/2. All raised to the exponent 4. This is the exponent 4, all raised to the 1/2. These are the same. So it doesn't matter where that exponent is, inside or outside, because it's a power, so you're multiplying. Here, we're taking the root of 9 and then raising it to the exponent 4. It's the same as raising 9 to the exponent 4 and then taking the root. Okay? What's good to know is if you have something like this, I would convert it to this. Way easier to take the root of 9 and then raise it to the exponent 4 rather than this, right? You probably need to use a calculator. Okay, so you can interchange which goes first. And then here, your general case. So the nth root of a, so we've been doing square root, so it's raised to the 1/2. If it was cubed root, it'd be raised to the 1/3. Fourth root, 1/4. And then if you actually raise the radicand to an exponent, that's going to be the numerator of that fraction. Okay. So we'll do some simplifying here. There's no numbers in the radicand. We're just simplifying. Okay, so this here, you can think about, I would, anytime there's a radical, convert it back to fractional exponents when we're dealing with variables. So this is the same as x to the 1/2 raised to the exponent 4. Then a power of a power, 1/2 times 4 is 2. Next one's already in power form, okay, exponent of 1/2. So multiply those together. 1/2 of 24 is 12. Okay. Here, this one got m to the 10, and then we're square rooting it, which is like an exponent of 1/2. Multiply those together. So really what you end up doing is dividing that exponent by 2 when you're square rooting it. Okay? Because when you multiply by 1/2, it's like dividing by 2. And then here, power of power, that'll just be 7. 14 times 1/2. Okay. A couple more questions on the next page. Okay, expressed as a single power, so again, use your laws. Check, they're the same base, so your base is 3, and then you're going to add 7/5 plus 3/5. Well, when you're adding fractions, you need the denominator the same, which it is, it's 5. 7 plus 3 is 10. Well, 10 over 5 is 2, so this is really 3 squared. Okay, it doesn't say to evaluate, but you can obviously equal to 9. And here, base is 11. Now you're subtracting, so this was adding. This is subtracting. So same denominator of 4. 13 minus 5 is 8. So that's squared as well. and 11 squared is 121. And then C, power to power, you're just multiplying exponents. So this is multiplying. A third times 18 is 6. I don't know what 8 to the 6 is. You can evaluate it. Didn't ask you to, but what is it? It is 8 to the 26. 262,140. Okay, next one does say evaluate. So you actually have to find that value. You want to see work. Okay, so sometimes on a test, you might ask you to evaluate. You can punch these all into your calculator. It'll do everything for you. So we will want to see work shown to get part marks. So this here, you could convert this to the 4th root of 16, okay, and then the cubed root of 27. Okay, that's one way to convert it to radical form. Or you could, because they're different bases, like we can't do anything right now with those exponents because they're not the same base. So we actually have to evaluate each part. Well, the 4th root of 16 is 2. And the cubed root of 27, that's pretty cute, right, is 3. So that's going to be 6. Right? You show another way. You could show 16 as 2 to the 4th, to the 1/4, and 27 as 3 cubed to the 1/3, and then you get an exponent of 1, an exponent of 1, and we get 6 at the end. These ones have the same base, so now we're going to subtract. Denominator 4, 5/4 minus 1/4 is 4/4, which is just 1. And if the exponent is 1, you don't need to show it. And then the last one here, we could raise a power to a power, okay, 27 to the 2/3, but that isn't evaluated. So let's think about, can we find the value of 27 to the 1/3? Well, that's the cubed root of 27. Okay, and we just did that over there. Cubed root of 27 is 3. So 3 squared is 9. Okay. Or you could go 27 is 3 cubed times raised to the 1/3, and then square that. Okay.